This is a 3 meter tall, 20 kilogram rocket that we sent to 3 kilometers just below the speed of sound at 2025's European Rocketry Challenge, where the best student rocketry teams in all of Europe meet each year in a friendly competition. This was our first time there, and it was also by far the most complex rocket we've ever built. In this video series, we're going to see how we went from our design to the launch pad and everything in between. This first part is about how we designed and built our rocket, and how we took an idea, turned it into a practical design, and how we turned that design into reality. Without any further delay, welcome to Project Stargaze. So let's say you want to build a rocket. If you break it down, it really isn't that complicated. You need an airframe to hold everything else together, some sort of engine to move it, a way to keep the rocket stable in flight, a method of releasing parachutes for landing, usually a flight computer, but very simple rockets can actually be purely mechanical as well. And finally, you need parachutes. That's about everything you need to launch a rocket, have it survive and come back in one piece. Of course, provided that everything goes as planned. But that is not how you get into EuRoC. To get accepted to compete, you have to bring a design that has actual value. As in, it needs to represent something that you actually have to do decent rocketry work to get to fly. It is a student rocketry competition after all. The point is to push yourself and gain experience that is actually useful once you're done studying and go to work in the aerospace industry. So a cardboard tube with a rocket motor inside is not going to cut it. We actually applied with an earlier version of Stargaze the year before and didn't get accepted until we improved it and tried again in 2025. The central question at the heart of every rocketry design or any engineering project really is, what are your requirements? The answer to that question will tell you everything that follows. If you just need something that goes up, you can work on a really simple design. But like we just covered, if you want to compete at EuRoC, you have to set yourself some proper goals. Some are already set for you by the nature of the competition. You can only choose to fly to either 3 kilometers or 9 kilometers, so your propulsion system has to be able to reach one of those altitudes. This also forces you into building a larger launch vehicle with at least an L-class rocket motor, because everything else just won't be powerful enough. EuRoC also has set requirements for recovery systems, such as no dropping parts that don't get recovered, and you have to keep the rocket from drifting away from the launch site too much. What adds to that are your own requirements. These can be pretty much anything, so I'm just going to say what we set out to do. First, the rocket has to withstand the forces of launch and flight with a very conservative safety factor on top. Second, it will carry our own flight computer alongside 2 commercial backups and the EuRoC quiet computer for a total of 4 flight computers on board. Third, it has to have a way of actively changing its apogee, specifically through increasing drag and therefore slowing down. Fourth, it also has to have a way of recording stabilized onboard video footage. Fifth, it has to use a recovery system consisting of a drogue and main parachute deployed by separating the nose cone. And lastly, it has to be able to charge its batteries while the rocket is still idling on the launch rail. Translated into design decisions, all of this means that we have to change a few things about how we build our rockets. All designs before Stargaze used a very similar, very simple design. They were made out of PVC pipe segments with a 125mm outer diameter, cut to length and bolted together using a set of aluminium couplers. That we had made by the aerospace workshop at the TU Berlin. This was strong enough to handle the relatively short heartburn of our second rocket, Stardust.
Ignition.
Stargaze would fly on a CTI M3700 rocket motor, bringing it twice as high, right up to the speed of sound, with twice the total impulse of our previous most powerful flight, which was on a CTI L1720. It will have to withstand over 30 Gs of acceleration, and like our requirement says, we want a decent safety margin on top of that, so we had to come up with something much stronger. So we abandoned the PVC airframe in favor of custom-made carbon fiber and glass fiber composites. Every segment of the rocket would be made out of 5 layers of carbon fiber weave, except the electrical compartment, which would be instead made from 8 layers of glass fiber to allow GPS and radio signals to transmit through it, since carbon fiber parts would effectively enclose the flight computers in a Faraday cage. These composite parts would then be epoxy bonded to aluminum coupler elements, which would then be bolted together. The fins would be permanently attached to this rocket. In the past, we went through designs that allowed us to remove and replace the fins for better logistics and the ability to tune the rocket for different flight profiles. But for Stargaze, strength is the most important requirement, so we decided to make the fins part of the motor compartment. They would contain a glass fiber core wrapped in the same carbon fiber weave that we used to make the other airframe segments. We have been working on making our own flight computer named the Max FC for quite some time now. Especially one of our members, who has since finished studying, really put tons of energy into this project, going as far as writing their bachelor's thesis about it, which is also why the computer carries his name. The idea is that we build a fully modular computer that can be customized to whatever mission you have in mind. It consists of a central compute module, specifically a Raspberry Pi Compute Module 4, and a set of modular add-on boards which all serve a specific purpose. There is a board for communication, there is one for measuring flight data, there is one for ignition, and so on. Whatever you need can be added, since all of these individual pieces communicate via a CAN bus, which allows tons of flexibility. Theoretically, if down the line we want to start doing active fin control, we could just design a board for steering a bunch of servos that takes in data from the flight data board, and we wouldn't have to change anything about the rest of the computer except adding software support. Beyond the Max FC, we are also carrying 2 Ultimax G4 flight computers. These serve as our backups, and we have used them on every launch we have ever done, so we know them very well and can be sure that they will work. We fly 2 of them rather than just one, because the Max FC is experimental, to the point that we don't trust it to do anything flight critical. Essentially, we treat the rest of the avionics as if it wasn't there, so we fly 2 Ultimax computers so that they themselves can be redundant. The last computer is a CATS Vega. This one is required to fly on every EuRoC rocket because it is used for in-flight telemetry by the organizers. This is also a fully functional computer on par with the Ultimax G4s, but since we haven't used it before, we made the decision to fly this as telemetry only, because we didn't see a reason to increase our workload and flight risk if we have a perfectly suitable platform that we have tons of history with right there. Often decisions in rocketry come down to what you know versus what you don't know. The CATS Vega is a perfectly fine flight computer that has worked great for lots of other teams. It wouldn't have become the default option for EuRoC if it hadn't. But for us personally, it represents an unknown that we can just decide not to deal with by sticking with what we know works for us. Especially if we are already deploying another new kind of flight computer that demands lots of time and attention. Stargaze will carry an Airbrake. This system can deploy 3 small surfaces in flight to increase drag, which will lower our apogee, which we purposefully aim to overshoot slightly. This way we can very precisely hit the 3 kilometers we set out to, which is one of the ways of collecting score points in EuRoC. Lots of other teams also have Airbrake systems, some of which are surprisingly similar to our own actually. It's a tried and tested way of guaranteeing you will hit one specific maximum altitude regardless of fluctuations in wind and stability and motor performance. Up to a point, of course. Even more fancy ways of flight control would involve active guidance with movable fins or even the ability to throttle your engine. But these are far more difficult and dangerous to implement, so you will rarely see them. We are in the beginning stages of designing our own engine and also have some ideas for embedding tiny control tabs in our fins, but that is definitely future stuff. We are not at a point where we can just do that yet. The Airbrake system has 2 control loops which are electrically independent of each other, meaning if one fails, the other should remain entirely unaffected. However, they do take sensor data from the same source, the Max FC, and they also control the same servo motor. EuRoC requirements expect your avionics to be fully redundant, and this represents a problem. Because how do you make a single motor truly redundant? The answer is you don't, and instead you plan for failure. We can't have two motors that would fight each other, but we can check if both control loops agree with each other, and if they don't, we know something is wrong. In this case, we can switch over to a failure mode, which commands the Airbrake to fully deploy for the whole flight. We do this instead of leaving it retracted because one of the rules of rocketry is that you never want to fly higher than necessary, and EuRoC actually reflects this in the scoring as well. Undershooting your target apogee deducts less points than overshooting it. You would rather make sure your rocket stays within known ranges than letting it go off uncontrolled, potentially flying out of your safety area and endangering someone else. Something that is just sort of accepted in rocketry is that onboard flight footage will have lots of rolling motion in it. This is because a fraction of a degree of misalignment in your fins can translate into several rotations per second once you apply the forces of a rocket launch. Unless your name is Stardust, in which case you have a perfectly stable flight despite it never being part of your design requirements. I guess Stardust was just built different. Until it hit the ground. And this is not even a bad thing. Having your rocket spin a bunch in flight increases its stability. If you played with Beyblades as a child, you know exactly what I'm talking about here. Spin them fast enough and they are remarkably stable. They can bump into things and just keep standing upright. But let them get slow enough and they just fall over. Having this stability bonus means you will arc over less, meaning you will fly higher, and it also means you can make your fin smaller, which reduces drag and again lets you fly higher. Counteracting the spin pretty much necessitates the presence of an active guidance system, which, like we just discussed, is not on the table for Stargaze. So, how do we get the spin-stabilized camera footage? You just despin the camera. Let the rocket roll as much as it wants. You only really need the camera to be stationary, the rest doesn't matter. This is something that you might have seen before on Joe Barnard's rockets. He has flown several camera spinner systems before, and the lessons learned from his attempts were undoubtedly helpful for our own design. Maybe results from our flights can help him or someone else to improve this idea even further. The cool thing about amateur rocketry is that it is largely a collaborative effort. While EuRoC is technically a competition, all the different teams gladly help each other out and share lessons learned and experiences to improve each other's designs. It is a very cool feeling to be part of this community where everyone supports each other. For instance, we actually didn't get our Katzberger flight computer on time because it got stuck in customs for like a whole month. So we actually ended up flying with one loaned to us by Team Tutsat, without whom we might not have made it to the launch pad. So huge thanks to you guys. This one is actually pretty simple because we have already been flying systems just like this. The only concerns are about fine-tuning it, since on Stardust the main parachute got stuck and didn't deploy, and on the following Moondust rocket we overcompensated a bit and actually let the main parachute yank itself free at apogee. The fix is to just tune the length of the various ropes that hold the parachutes and making sure through lots of testing that both parachutes always deploy as intended. The deployment system is based off flash cotton, because legal restrictions in Germany mean we can't use black powder or any other high-efficiency pyrotechnic devices for separating the nose cone. Flash cotton ignited by fireworks igniters are pretty much the only way to use explosive force for separation without breaking any laws here. We could use gas pistons or electrical systems instead, but that would be complicated and heavy, so we just accepted that it's the best we have access to. The nose cone is attached with 4 nylon screws that act as shear pins, meaning that once the flash cotton is ignited, these screws are designed to break and let the nose cone be ejected from the recovery compartment. This also pulls out the drogue parachute, while the main stays attached to the recovery compartment until at least one of 2 tender descenders fire at a few hundred meters above the ground, which releases a hold-down wire that lets the main get pulled out by the drogue parachute. We do all this because letting it fall without a drogue at first and then releasing the main would almost certainly rip the parachute apart, and maybe also parts of the airframe if the shock load is bad enough. And we can't deploy the main at apogee because the rocket would fall so slowly that it could drift very far away depending on wind conditions, and EuRoC requires you to land within a certain range from the launch pad. When it comes to batteries on smaller flight vehicles, you generally tend to see one type of battery pack above all others: lithium polymer. These are great because they are relatively lightweight, have a high voltage per cell and can put out lots of current. However, these characteristics also make them very good at starting fires. Which is why we are not allowed to use them on rockets where lots of highly flammable and explosive propellant is in close proximity. Instead, we have to use nickel metal hydride batteries. These are heavier, hold only about a third as much voltage per cell, and also charge and discharge at much lower rates. In short, you need to bring a very large battery if you don't want to run out of power while you wait for launch clearance. And wait, you will. It is rarely as easy as arming the rocket, getting to safety and then launching. Because of time constraints, EuRoC teams launch in waves. So you will have several rockets being prepped for launch at the same time. And unless you go first and encounter absolutely no issues, you can be looking at up to several hours of on-pad holding time before you can actually launch. Bringing enough electric charge to last this long with your entire avionics stack active is a real problem, because there's only so much space and only so much extra weight you can carry without having to change the engine and other parts of your rocket to compensate. Because of this, we decided to add on-pad charging capability. We can bring a massive battery that will last us hours no problem and then connect it to the rocket through magnetic cables that just let go when the rocket launches, making sure we are topped up and have absolutely no way to run out of power mid-flight or even dropping our voltage so low that it's not enough to light the igniters for the recovery anymore, which would instantly kill the flight. This is known as the rocket going ballistic, and this actually happened to several other teams at EuRoC. While it is unfortunate for them, it shows that we probably made the right decision with this. And with that, we've covered all of our requirements. Now that we know what we want to build, it is time for the next question. How do we build it? The first part of Stargaze we built was the airframe. While we had actually made composite parts before, the nose cone used on Stardust was made out of glass fiber, we were not happy with the end results, and the process was also rather long and labor intensive. So we decided to try something new. The very first attempt at this actually started long before Stargaze was even completely finished in design with the Moondust rocket. Moondust was originally just meant to be a copy of Stardust with a revised recovery system following its main parachute failure, but it was soon expanded into a testbed for some of the new ideas we wanted to implement for Stargaze. Specifically, we tested our new ideas for manufacturing the nose cone and the fins, while the other aspects were still being worked out. This ended up being very useful for gaining experience and learning lessons about how to best work with composite materials. Without the Moondust test run, we probably would have run into a lot of problems where we absolutely could not afford to. So I am glad we ended up testing so much. There will probably be a dedicated video about Moondust one day because it in itself is also an interesting story, but covering it here would explode the runtime of this series more than it already has. So let's just talk about how we built Stargaze. We made the nose cone using two negative mold halves that were 3D printed and then had their surface smoothed with UV resin. This is not the best method to do it at all, but this is what we did for Moondust, and we would rather just reuse a method that we know works okay-ish than have to reinvent a whole new process. 3 layers of carbon fiber weave were cut out for each side and then laid up inside the halves after they had been coated in PVA mold release. These 2 halves were then attached together while the epoxy cured, and a few days later we had our nose cone. Because the carbon fiber weave we had used is rather thick, we had larger defects on the seams between the halves, which had to be fixed with gap filler before we could continue. Then we cut the top and the bottom off to give us a nice even edge for attaching the tip and coupler. The tip is made out of PEEK, which is a high strength, high temperature plastic because EuRoC does not allow metal tips. This tip is attached with a 3D printed wedge piece that is sandwiched between the tip and the eyebolt that pulls out the drogue chute when the nose separates. The coupler uses a common design that we used all over the rocket. It is made out of aluminium, and together with the PEEK tip and the other coupler parts we have these machined by the workshop at the Institute of Aerospace of the TU Berlin. The coupler has a lip that is then epoxy bonded to the nose cone, and with that we have the first Stargaze part. Time for... Before we can talk about the fins, we need something to attach them to. By the time we made the Airframe Tubes, we already knew that a nose cone manufacturing process was less than ideal, so we decided on a different approach. All of our airframe sections were made as one solid piece in a positive mold process that used 8 glass fiber layers, for the electrical compartment and 5 carbon fiber layers for the motor and recovery compartments. All of this was based around a metal tube that we had machined down to exact tolerances by the Institute workshop, which we then covered in a layer of mylar sheet below a layer of PTFE tape. The idea was that these two insulation layers would prevent the part from bonding to it, which we would then be able to just pull out once the epoxy had cured. This worked, for the most part. We did get the recovery and electrical compartment tubes off without much trouble, but the motor compartment, however...
Oder? Ich hab's schräg.
We tried very hard, but it just wouldn't move past a certain point. The eventual solution was perhaps just as funny as the problem itself, because what we ended up doing is getting a big fridge and putting the entire thing in there until it was very cold. We then took it out and hammered the inner tube out bit by bit over the course of several days until it eventually finally let go. All the pieces then also had their top and bottom trimmed to size, holes cut into them, and got their couplers bonded. The motor compartment also received some 3D printed spacer rings since it is very long, and these would help with inserting the Pro 75 6-grain case which would house our rocket motor. Now that we have our airframe done, we can make our fins. These were first cut out of a 4mm thick glass fiber sheet, after which we promptly dropped one of them, which caused it to deform. Thankfully we had enough left over to make one more spare, so we avoided a major problem right there. We sanded the edges to be the same between all three and then 3D printed a fin jig to press the fins onto the motor tube for root bonding, using the same high strength epoxy we used to attach the couplers. 48 hours later, it is now time to make some fillets. For this I mixed together some of our laminating epoxy with some micro balloons. These are tiny hollow glass spheres that help to thicken up your epoxy mixture so it holds its shape better. Doing this plus waiting around 30 minutes to let the epoxy begin to harden slightly lets you do some very nice fillets using some 3D printed filleting tools. We wanted to do all sides at once, so we couldn't let it sit on the side. This had the effect that while the epoxy is now much thicker than usual, it still slowly flows over the course of a few hours. We knew this would happen and planned accordingly, and after letting it sit for another 2 days we returned to find out that the fillets had indeed flowed slightly out of shape. We used a Dremel to remove the excess and then sanded all the surfaces in preparation for the fin layup. Each side would be covered in 3 layers of carbon fiber weave in different sizes. We did this because we learned from Bundas that doing all layers at full size caused the lowest layer to delaminate when the top layers cured and shrunk slightly. So here we used 3 different sizes, chosen so that if one layer delaminates, the other 2 still cover a large amount of the fin area. Once the layup on all 3 sides was done, we again waited 2 days and then got to trimming the axis to get the nice clean outer edge. At this point the rocket was really starting to take shape, which was good because at this point it was less than 3 months until EuRoC'. The only big ticket item left on the mechanical team's to-do list at this point was the smaller diameter tube that the camera spinner payload would sit around. The structural rocket diameter drops from 125mm to 75mm at this point, which means this part of the rocket needs to be very strong. It almost exactly sitting in the middle of the rocket didn't help either. The couplers here were really beefy, and they had to be. This is the point of the rocket where we have the highest structural loads. Consequentially, the payload tube would also have to be very, very strong. I'm just going to cut it short here. We did try to make our own payload tube. It would have had something insane like 8 or more layers of carbon fiber, and it was also meant to be made in a very similar way to the nose cone since it had to have a very precise outer diameter. But this didn't really work. We tried several times and never managed to produce anything usable. The tolerance requirements were just above our skill level. It didn't help that we later found out that we also needed a very precise inner diameter as well, which we weren't aware of before. So, long story short, we just bought one. Once it arrived, we drilled all the holes in it and attached the mounting points, and with that, we had our payload tube. Okay, now we have all the airframe parts, but they don't really look like we want them to. Usually rockets are painted in a high visibility color scheme so that they are highly visible. This helps with tracking them in flight and also finding them for recovery. And as you can imagine, EuRoC does have corresponding requirements. It was decided that we wanted a white-red color scheme for Stargaze, which of course means that we need to paint it. So just get some spray paint and slap it on there, right? Not so fast. The surfaces of our parts, especially the airframe tubes, were covered in lots of tiny pockmarks. These don't look so bad without any paint, but once it's on there, these really look downright awful. So we need to do something about that before we can do any painting. The solution to this is to coat all the outer surfaces with a layer of hardware store gap filler. This will fill in all the tiny voids in the outer surface, and it's a soft enough material to easily sand away any excess. So we took all of our airframe parts downstairs and started gap filling. This is also the fourth time at this point that we had to do a significant amount of hand sanding, and you can tell we are not so happy about it anymore.
Oh, wie viel Staub hier abgeht. Boah. Oh.
We spent almost an entire day sitting down there sanding the surfaces, and we didn't even get close to done. It was late in the afternoon that we were finally saved from hand sanding hell when one of our members brought their orbital sander from home, and following this all sanding work was completed within a few hours. The next day I was homesick, but the rest of the team continued working and managed to paint all the airframe sections, and it looked so much better now. I did not think we would ever have a surface finish as smooth as this. This paint job easily makes the rocket look more professional. There were no pockmarks visible anywhere. The surface isn't perfectly flat, you can still see that it was definitely handmade, but the rocket looked so much better, even up close. All that we just went over is something that I was personally part of. Because of that, I naturally had the most say here and also the most footage. But the other Bears members were working hard on their parts of the project too. In parallel to all of this, our electrical team was working hard on the Max FC and the internal design of the electrical compartment, which consists of several 3D printed mounting adapters designed to hold in all the batteries and flight computers the rocket will need. A rocket path simulation was made by the software team, lots of payload testing was underway, the Airbrake slowly took shape, and overall every team made steps towards launch. The mechanical and recovery teams were pretty much ready to go at this point, and payload was also in the finishing stages. What still needed work was the electrical system and specifically the flight computer. Software for it could only be written once the hardware was done, and the hardware was at this point still in the prototyping phase. Because the Airbrake depends on sensor data from the Max FC, it was also being held back somewhat. We expected our 2 weeks in Portugal would probably not be a vacation with a rocket launch attached, but rather a lot of final launch prepping and testing. So extra time for software development was already planned for. It was just becoming apparent that it was probably going to be a rather close shave. For now, there was not much we could do about it. The electrical team just needed time to finish their work. But what we could do, since physically the rocket was very close to finished, was integration testing. And oh man, there was a lot of integration testing. By now we have finished the airframe, acquired a motor case and a dummy weight for it, got the internal structure of the electrical and payload compartments, mostly final, and got a complete recovery compartment. This is good enough to perform something we call a cold start, where we pretend to ready the rocket for flight according to our checklists and procedures. If we have time, we'll even assemble a launch rail and go through the actual launch process just without a rocket motor installed. For now, that second part depended a bit too much on the flight computers being fully ready, so we skipped that, but we could easily take all the parts that we have, put them together and see if everything works as intended. This was done several times during the last few weeks before launch, since every time you do it, you don't just find small problems like a screw being too long or too short or a 3D printed part not fitting the tolerances. If we get used to putting this rocket together by just doing it a lot, we will naturally get better at doing it. We'll do it more efficiently and make less mistakes each time. This is very useful when it's launch day and you need to solve some unexpected problem that came up, which can eat a lot of time, potentially causing you to miss your launch window. This did happen to at least one team at EuRoC after their rocket continuously encountered problems, delaying the launch until there just wasn't any more time to launch. this is also where I recorded a lot of footage. There was one night where we stayed up well into the next morning while we were doing our final cold start before it was transporter packing day, and I think I just want to give you a look into how that went.
So, gut, dann Airbrake, kannst jetzt auch einen Check machen.
Airbrake. Assembled Airbrake compartment, check.
Okay, so, dann.
Okay, done. General integration checklist. Task 1. Check previous checklists and completion of compartments.
Gut.
Fail.
Das ist auch Fail.
Okay. F for fail.
Eigentlich würden wir so alles kontrollieren hier, aber es gibt nichts zu kontrollieren. So, Motor kommt jetzt mal rein. Okay, ich glaube. Ja, der Täter.
The nose got knocked with a double figure 8 knots to the swiveling and
Ja, genau, das
machst du
bei
gerade.
Pre-Flight. Bei Pre-Flight würde ich das machen, oder?
Okay, genau.
Alles, was wir da drin umfingern, bewegen uns nur hinterher. Da legen wir es hier rein. Eine Schallkasten? Ist es jetzt der Schallkasten, den wir vermeintlich geflasht haben? Kaputt gemacht haben? Also haben wir nicht kaputt gemacht.
Ja, funktioniert. Ich denke mal, der Powercon wird dann irgendwie abgefangen. Der hat bestimmt eine Sicherheit.
Okay, Niklas, dann begeh mal dein Verbrechen. Also,
Ingenieure sein.
was machst du mit dem Schraubenziehen?
Steckst du doch über erst? Ist es schon angeschaltet oder?
Nein.
Ach du Scheiße. Nee, oder? Nee. Warum waren da gerade 22 Volt?
Das ist normal.
Was ist das so normal?
Also jetzt haben wir kein Seilproblem mehr, aber wir haben ein Kabelproblem.
Sicher 10 cm zu lang.
Ja. Es hat aber trotzdem erstaunlich gut funktioniert. Also minus, dass wir die Kabel nicht verbunden haben.
Also die Kabel sind jetzt noch verbunden, ja. Einmal kurz aufstecken. Jetzt steckt mich davor und dann. Wenn die Rakete ist, erschreckst du dich.
Nee, mach mal nicht.
Ja, geht doch. Weiter ein bisschen wackeln.
It is now less than 4 weeks until launch day, which means it is time to bring all of our equipment to Portugal. For this, we rented out a small transporter that would drive the whole 6,000 kilometers there and back, carrying the bulk of our hardware, since the rest of us would be flying in and could only bring small bags with personal items. The flight computer was still not fully done, so it was decided that, since the transporter would need almost 2 weeks to drive all the way there, the flight computer hardware, which is small enough to fit in a personal bag on a flight, would stay with us for now to give us some more development time until the rest of the team would board their flights. Speaking of that, since we want to keep costs low, we ended up flying on a low-cost carrier with multiple tickets booked separately, meaning we would first have to fly to France and then board a new plane there that would bring us to Portugal. Not really a huge issue, but just a little annoying, and it can get kind of dangerous if your first flight ends up delayed by a lot, because those separately booked tickets do not have any money back or replacement flight guarantees if you miss your connecting flight. But there's not really anything we can do about that, so on the 3rd of October 2025, all of us took our luggage and we went to Berlin-Brandenburg Airport to begin our journey. And what happened then will be in part 2 of this series, where we discuss launch preparation, testing, ground station development, and how on one fateful night we absolutely did not get stuck in France. I hope you enjoyed this first look into how our EuRoC attendance went, and I'll see you in part 2.